Welcome back to the channel, Explorers of the Cosmos. Tonight, we are about to attempt something that sounds simple, but may be one of the most impossible journeys humanity could ever imagine. Look up at the night sky for a moment. That faint, glowing band, stretching from one horizon to the other, is not just a beautiful pattern of stars. It is the visible edge of an enormous cosmic city. A rotating spiral system containing hundreds of billions of suns, countless planets, vast rivers of gas and dust, and mysteries that scientists are still struggling to understand. This is our galaxy, the Milky Way. And today, we are going to ask a question that sounds almost like science fiction, yet is deeply rooted in real physics and astronomy. How long would it actually take us to cross it? At first, the idea might seem straightforward. Humanity has always been a traveling species. We crossed oceans, deserts, and continents. We built machines that fly faster than sound and spacecraft that can escape Earth's gravity. So naturally, the next step feels inevitable. One day, we will travel between stars. But the moment we begin to examine the true scale of our galaxy, the illusion of simplicity collapses. Because the Milky Way is not just big. It is so overwhelmingly vast that even light, the fastest thing in the universe, needs around 100,000 years to move from one edge to the other. This single fact already begins to stretch the limits of imagination. To understand what it means to cross our galaxy, we must first understand what our galaxy really is. The Milky Way is a barred spiral galaxy with a diameter estimated at roughly 100,000 light-years. This means that if you could somehow stand at one extreme edge and instantly teleport to the opposite side, the distance you traveled would equal the distance light covers in 100,000 years. But light does not slow down. Nothing in the known universe can move faster. This means that any physical journey, any spacecraft, any probe, any human expedition would inevitably take longer. Our galaxy is also not a flat disk like a sheet of paper. It has thickness. In the central regions, the galactic bulge swells outward with dense concentrations of stars. In the outer regions, spiral arms stretch like cosmic highways, curving gracefully around the center. These arms are not solid structures. They are patterns of motion, mid-density waves where stars form and drift over millions of years. Between these arms lie vast stretches of interstellar space, where the nearest star might be several light-years away. When we speak of crossing the galaxy, we are not talking about navigating through a crowded field. We are talking about traversing a desert so immense that entire solar systems become rare islands of light. Our own position within this enormous structure adds another layer of complexity. The solar system resides in a minor spiral feature known as the Orion Arm, located approximately 26,000 light-years from the galactic center. From here, we orbit the center of the Milky Way at a speed of roughly 800,000 kilometers per hour. This sounds incredibly fast, yet even at this speed, it takes the Sun about 225 million years to complete a single orbit. To put this into perspective, the last time our solar system occupied this exact position in the galaxy, Earth was dominated by early dinosaurs. Humanity did not exist. Mammals were tiny creatures hiding in shadows. Civilizations were unimaginable. Galactic motion operates on timescales that dwarf biological evolution itself. So what does it really mean to cross the galaxy? There are multiple possible paths. One could attempt to travel directly through the galactic disk from one edge to the other. This would require navigating regions of varying stellar density, molecular clouds capable of forming new stars, and remnants of ancient supernova explosions. Another possibility would be traveling radially, heading toward the galactic center and then continuing out the opposite side. But this introduces even greater dangers. The central region of the Milky Way is dominated by extreme gravitational forces and intense radiation environments. At its heart lies a supermassive black hole known as Sagittarius A star, containing millions of times the mass of our Sun. Surrounding this region are tightly packed stars moving at tremendous velocities, along with energetic phenomena that could threaten any hypothetical spacecraft. Even choosing the direction of travel becomes a complex scientific problem. Space is not empty in a practical sense. While collisions between stars are extraordinarily rare due to the vast distances separating them, smaller hazards are far more common. Microscopic dust grains traveling at high velocities could strike a spacecraft with devastating energy. Charged particles accelerated by cosmic magnetic fields could gradually erode materials and disrupt electronics. Regions of intense star formation might flood surrounding space with radiation capable of damaging biological organisms. In other words, crossing the galaxy is not simply about distance. It is about survival within a dynamic and sometimes hostile cosmic environment. Another crucial factor is the distribution of matter within the galaxy. Stars are not evenly spaced. Near the galactic center, stellar density increases dramatically. In these crowded neighborhoods, gravitational interactions between stars can alter planetary orbits and destabilize entire solar systems. Farther out in the galactic disk, stars become more isolated, being separated by larger expanses of interstellar medium. This means that a journey across the galaxy would involve constantly changing conditions, from relatively calm regions to zones of intense gravitational complexity. Any long-term expedition would need to adapt continuously to its surroundings. Scale visualization can help us grasp this overwhelming reality. Imagine shrinking our entire solar system, including the orbit of Neptune, to the size of a small coin. At this scale, the Milky Way would still be larger than an entire continent. Traveling from one side to the other would be like attempting to cross thousands of kilometers of wilderness, except every step represents millions of years of travel. This analogy is imperfect, yet it highlights a fundamental truth. Our intuitive understanding of distance breaks down completely at galactic scales. Even the stars themselves are in motion. As we journey across the Milky Way, we must remember that our destination is not fixed. Over tens of thousands or millions of years, stars drift along their own orbital paths. Spiral arms shift. Molecular clouds collapse to form new stars, while older stars explode as supernovae. The galaxy is alive with change. A spacecraft attempting to cross it would not be traveling through a static map, but through a constantly evolving landscape shaped by gravity and time. Understanding this dynamic structure is essential because it reveals why the question, how long would it take to cross our galaxy, cannot be answered with a single number. The answer depends on direction, speed, technology, and the ability to endure conditions that humanity has never experienced before. What begins as a simple curiosity becomes a profound exploration of physics, engineering, and the limits of intelligent life. As we stand on our small blue world and imagine such journeys, it is easy to forget how recently humanity entered the space age. Just a few decades ago, reaching the moon was considered the ultimate challenge. Today, robotic probes are venturing beyond the boundaries of our solar system. Each technological step expands our horizon slightly further. Yet when measured against the scale of the Milky Way, even our greatest achievements remain microscopic. Crossing the galaxy is not merely the next step in exploration. It is a leap so vast that it may require entirely new forms of existence. And this realization leads us naturally to the next critical question. If the galaxy is this enormous, how fast would we need to travel to cross it within a meaningful time? Would current spacecraft take thousands of years, millions, or longer than our species could survive? To answer this, we must now shift our focus from the structure of the Milky Way to the limits of motion itself. Because the true challenge of crossing our galaxy is not just distance, it is speed, and the unforgiving laws of physics that define what is possible. In the next part of this journey, we will calculate exactly how long it would take to cross the Milky Way, using real spacecraft velocities, theoretical propulsion systems, and even relativistic travel near the speed of light. The numbers we are about to encounter will not just surprise you. They may fundamentally change the way you think about humanity's future among the stars. As we continue this extraordinary journey across the scale of our galactic home, we now arrive at the most critical and unsettling part of the question. Understanding the size of the Milky Way is one thing, but truly grasping how long it would take to cross it requires us to confront the limits of motion itself. Distance becomes meaningful only when paired with velocity. 1,000 kilometers can be crossed in minutes by an aircraft. 1,000,000 kilometers can be crossed in days by spacecraft. But when the distances stretch into tens of thousands of light years, even the fastest technologies humanity has ever built begin to feel painfully slow. Let us begin with the reality of present-day space travel. Humanity's most distant explorers are not astronauts, but robotic probes. Among them, the Voyager spacecraft represent one of the greatest engineering achievements in history. Launched in the late 20th century, these machines have traveled farther from Earth than any human-made object ever before. Moving at speeds of around 17 kilometers per second, Voyager 1 has now entered interstellar space, leaving behind the protective bubble of the sun's influence. It is drifting through darkness, carrying with it a golden record intended for any distant intelligence that might one day discover it. Yet when we place this incredible journey within the scale of the Milky Way, its progress becomes almost invisible. At its current velocity, Voyager would require roughly 70,000 years just to travel the distance to the nearest major region of our galaxy. To cross from one side of the Milky Way to the other would take nearly 2 billion years. This is not merely a long time. It is a duration comparable to the age of complex life on Earth. Entire ecosystems have risen, transformed, and vanished within such spans. Continents have shifted, atmospheres have changed, species have evolved beyond recognition. A spacecraft taking this long to complete its journey would outlive the very civilization that launched it. Recognizing this limitation forces us to imagine more advanced propulsion systems. Nuclear propulsion represents one of the first major leaps beyond chemical rockets. By harnessing the immense energy locked within atomic nuclei, nuclear thermal engines could propel spacecraft with far greater efficiency. Such systems might allow velocities several times higher than current probes, reducing interstellar travel times from tens of thousands of years to perhaps a few thousand. This improvement is dramatic, yet still humbling. Even with nuclear technology, crossing the galaxy would remain a journey measured in millions of years. More ambitious concepts aim to unlock the power source that fuels the stars themselves. Fusion propulsion, still under development in laboratories on Earth, offers the possibility of sustained high-energy thrust capable of accelerating spacecraft to a significant fraction of the speed of light. If a vessel could reach 10% of light speed, the time required to cross the Milky Way would fall to roughly 1 million years. For the first time, the numbers begin to approach scales that feel marginally conceivable in the context of cosmic history. Yet, even this achievement would require technological stability and social continuity far beyond anything humanity has yet demonstrated. At even higher velocities, approaching half the speed of light or more, the strange consequences of relativity begin to reshape our understanding of the journey. According to modern physics, time is not absolute. For travelers moving at extreme speeds, the flow of time slows relative to observers at rest. This means that a crew crossing the galaxy at near light velocity might experience only a few decades or centuries, while tens of thousands of years pass elsewhere. In effect, such explorers would become travelers into the future, arriving in a galaxy that has evolved far beyond the one they departed. But achieving these speeds introduces staggering energy requirements. Accelerating a spacecraft to relativistic velocity would demand resources comparable to the total energy output of entire civilizations. Managing such power safely would require revolutionary advances in materials science, engineering, and perhaps even new discoveries in fundamental physics. The challenge is not simply building a faster engine. It is transforming the technological foundation of intelligent life. Another fascinating possibility is the idea of generation ships. Instead of attempting to complete the journey within a single lifetime, a spacecraft could function as a self-contained world. Families would live, reproduce, and die aboard it, passing the mission down through countless generations. Over thousands of years, the descendants of the original crew might finally reach distant regions of the galaxy. Such voyages would redefine exploration as a cultural and evolutionary process, rather than a temporary expedition. The ship itself would become a moving civilization, carrying its history across the stars. Yet speed and endurance are not the only challenges. As velocity increases, the environment of space becomes increasingly hostile. Tiny particles of dust, harmless at low speeds, transform into lethal projectiles when encountered at relativistic velocities. Impacts with these grains could release enormous amounts of energy, threatening to destroy even heavily shielded spacecraft. Cosmic radiation presents another danger, and streams of high-energy particles traveling through the galaxy can damage biological tissues and electronic systems, gradually degrading the ability of travelers to survive and navigate. Despite these obstacles, the dream of crossing the galaxy continues to inspire bold theoretical ideas. Some physicists speculate about the possibility of shortcuts through space-time itself. Wormholes, hypothetical tunnels connecting distant regions of the universe, could allow travelers to bypass the immense distances between stars. If stable wormholes could be created or discovered, crossing the Milky Way might take days or even minutes rather than millennia. However, such concepts remain speculative, requiring forms of matter and energy that have never been observed directly. For now, they belong more to the realm of mathematical possibility than practical engineering. Another intriguing approach involves the use of artificial intelligence and autonomous probes. Instead of sending fragile biological organisms across vast distances, humanity might deploy fleets of intelligent machines capable of surviving extreme conditions for indefinite periods. These probes could replicate themselves using local materials, spreading gradually throughout the galaxy like seeds carried by cosmic winds. In this scenario, crossing the Milky Way becomes less about transporting individuals and more about extending the reach of knowledge and awareness. As we reflect on these possibilities, one profound realization begins to emerge. The question of how long it would take to cross our galaxy is not simply about numbers. It is about identity. And if a journey requires thousands or millions of years, the travelers who complete it may no longer resemble those who began it. They may be genetically modified, cybernetically enhanced, or entirely artificial. Crossing the galaxy may require humanity to evolve beyond its current form, transforming into a civilization capable of existing on cosmic timescales. And yet, even after confronting distances that dwarf imagination and speeds that challenge the limits of physics, we arrive at a deeply philosophical conclusion. The Milky Way is both our home and our horizon. It is vast enough to inspire awe, yet structured enough to invite exploration. Somewhere among its hundreds of billions of stars may exist other civilizations asking the same questions, dreaming of journeys that span the spiral arms of their shared cosmic city. Perhaps the true meaning of crossing the galaxy is not reaching the opposite edge. Perhaps it is the act of striving itself, the refusal to remain confined to a single world. Humanity's history is defined by exploration. From the first steps out of ancient forests to the launch of interstellar probes, our species has continually expanded its boundaries. The galaxy represents the next great frontier, one that may take thousands of generations to fully comprehend. So the next time you look up at the Milky Way stretching across the night sky, remember that you are witnessing a structure so enormous that even light struggles to traverse it within a single cosmic lifetime. You are standing at the beginning of a journey that may never truly end. Because crossing our galaxy is not just a challenge of engineering or physics. It is a challenge of imagination, resilience, and the willingness to redefine what it means to be human. If this journey across the impossible distances of our galactic home expanded your mind and sparked your curiosity, make sure to subscribe and join us for the next exploration. Because beyond the spiral arms lie even greater mysteries. Supermassive black holes, cosmic voids, and phenomena that may reshape our understanding of reality itself. Until then, keep looking up, keep asking questions, and remember that somewhere in the vast darkness of the Milky Way, the future of exploration is already waiting.